You know how a paperclip, when you bend it back and forth, always seems to break in the exact same spot? Or why a tiny chip in your phone screen can suddenly spiderweb across the whole thing? Well, it's not random. It's physics. It's all about a concept called stress concentration. And once you understand it, you'll start to see the hidden reasons why things break exactly where they do. This idea, believe it or not, was captured perfectly way back in 1858 in a poem about the wonderful one-hoss shay. The goal of the poem's hero, the deacon, was simple but pretty profound. He wanted to build a carriage where the weakest place, that one spot destined to fail first, was just as strong as every other part. He was chasing the dream of a perfectly balanced design. So the one-hoss shay was this legendary carriage, an engineering marvel so perfectly proportioned that no single part was weaker than any other. It was designed to last forever, or, as the poem says, to fail all at once and nothing first after exactly 100 years. It really is the perfect ideal, right? But let's be real, that's a poetic ideal. In the actual world of engineering, whether we're talking about bridges or bolts, things almost always have a weak spot, a single point that is absolutely destined to fail before anything else. The real question is, what creates that weak spot in the first place? Okay, let's meet the villain of our story. Engineers have a name for it, a stress raiser, or sometimes a stress concentrator. And really, it's any feature in a part's geometry that forces stress to build up right around it. And the thing is, they are everywhere. And what's wild is just how common these features are. A simple hole you drill in a plate, the threads on a bolt holding your desk together, a little groove for a rubber O-ring to make a seal, even the shoulder on a shaft where it changes diameter. All of these everyday design features are secretly concentrating stress. Here is a brilliant way to visualize what's happening. I want you to imagine the stress flowing through an object like it's water in a river, or maybe lines of force. Now, if the object is a smooth, solid bar, those lines flow nice and evenly. But the moment you put an obstacle in the way, like a hole, the lines of force can't go through it. They have to squeeze around the edges, crowding together. That crowding, that is stress concentration. So, if the stress raiser is our villain, then the hero of our story is this, the stress concentration factor, which we call KT. Now, KT isn't just some vague idea. It is a hard number. It's a multiplier that tells engineers exactly how much more intense the stress is at that one tiny point compared to the average stress in the rest of the material. And the formula? It's beautifully simple. KT is just the maximum concentrated stress right at the flaw divided by the nominal, or average stress in the area. The nominal stress is what you'd calculate if that hole or notch wasn't even there. So KT is the magic number that connects the simple theory with the dangerous reality. And this illustrates the concept perfectly. On the left, you've got the simple textbook idea of a single notch. On the right, a real-world gear tooth. But look closely at the base of that tooth. What is it? It's just a series of notches, one after another. Every single one is a potential failure point. Understanding the KT of that curve is absolutely critical to designing a gear that won't snap. So, where do engineers get these magical KT values? Well, for decades, the answer has been one single book, Peterson's Stress Concentration Factors. It is the definitive encyclopedia, with hundreds of charts covering pretty much any shape you can possibly imagine. And let's put a face to the name. This is Rudolf Earl Peterson. For about half a century, he was known as Mr. Stress Concentration. His entire life's work was to painstakingly collect, calculate, and catalog all of this critical data so that other engineers could design things safely without reinventing the wheel. Now, a chart like this, I know, it can look a bit intimidating at first glance, but it is an incredibly powerful tool. Each one of those curved lines represents a slightly different shape, and it lets an engineer find a precise KT value for their specific part without having to run a bunch of complex calculations from scratch. So how does an engineer actually use one of these? It's a surprisingly straightforward four-step process. You start with your part's geometry, just simple ratios like the radius of a corner versus its depth. You find that ratio on the bottom axis, you trace up to the curve that matches your part's shape, and then you just trace over to the left and read the KT value right off the side. Peterson did all the hard math so engineers could get a critical safety number in seconds. So let's say you go through all that and you get a number, like KT equals 3. What does that actually mean? It means that at the very root of that tiny little notch or hole, the material is feeling stress that is 3 times higher than the material just a little bit away from it. It's a massive amplification in a tiny, tiny area. And that is why failure starts right there.
Okay, so you might think the story ends there, right? Find the KT, design for it, and you're done. But there's a fascinating twist to this whole tale. And it all comes down to the type of material you're actually using.
Right. This is where the material itself completely changes the story. On one side, you have brittle materials, like glass. For them, the rule is simple. Stress builds up at the tip of a crack, the KT factor is king, and the glass shatters. But for a ductile material, like steel, something amazing happens when it's under a steady load. That single point of super intense stress actually yields. The metal deforms just a tiny bit, which has the effect of blunting the sharp point of the stress razor. That tiny deformation lets the stress spread out more evenly to the material around it. The material literally saves itself from breaking. So, because of this incredible self-relieving effect, when dealing with static loads, engineers will often just set KT equal to 1, which means they basically ignore it for two specific cases. First, for ductile materials that can stretch more than 5% before they break. And second, weirdly enough, for gray cast iron, which is so full of tiny internal graphite flakes that it's already packed with stress razors, so adding one more just doesn't make a big difference.
And this brings us full circle, right back to the deacon's poem. His goal was to make that place as strong the rest. But modern engineering takes a more nuanced approach. It's not just about beefing up the weak spot by adding more material. It's about deeply understanding the nature of that weakness. So the modern design philosophy isn't about avoiding weak spots. It's about mastering them. It's a clear process. First, you identify the stress razors. Second, you quantify their effect with the KT factor. And third, you design intelligently with that knowledge. Maybe that means smoothing out a sharp corner or choosing a more ductile material. This is how we create parts that aren't just strong, but are also lighter, safer, and way more efficient. So in the end, we can finally achieve that ideal of the one-hoss not through brute force, but through intelligence. By understanding exactly where and why the weakest point exists, we can design entire systems where every single component is used to its full safe potential. A perfectly balanced design, achieved through knowledge. So I'll leave you with this question. Now that you can see these hidden stress points all around you, in the handle of a coffee mug, the corner of a window frame, the little bracket holding up a shelf, what's the weakest place in the next thing you build or design?